current is an automatic adjustment as a result of R and VDD. Or you, as an engineer, when you design and you want some current, then you will go and select accordingly VDD and R. But if you have a circuit, right, with some VDD and R, and you place a diode like this will, it's not that we have to do some fine tuning. This is an automatic current that will come, that will be flowing. Okay, so that is how the nature works. The nature is smart enough that it will only flow that current which satisfies both of this equation. But tomorrow, if you have to design and you have a requirement that I need this much current, right, then accordingly you have to vary your R and VDD. But irrespective of this, when you vary VDD from 0 to some value, you will get the same graph of the diode. Okay, so that is one thing, and this is the operating point. So now in that example, what is given to you in this example for the same thing, now you imagine, keep it in your mind, right? What is given to you, I should right, so what is given to you is that for this circuit, determine the current ID. So ID you have to find out, and the diode voltage VD. So that voltage across diode is VD. So for this, okay, a VDD is given, R is given. Assume that diode has a current of 1 milliamp at 0.7. Now see, when this is given, right, the voltage can be, it can be, I'll show you, and its voltage changes by 0.1 for every. Now this difference is given. So what it is telling from, if you just think of, I go back to this, ID, VD, you have to find out for this values of this. And it is saying, so see, for this conditions that is given to you, yeah. See, for this condition that is given to you, you have to find out this ID and VD. Now, this ID and VD can be, now this ID and this VD, this VD can be, let's say, 0.75. Okay, it can be, that is what we have to find out. So it can be 0.75, 0.71, 0.72, or 0.701, whatever. And some value. So this graph will have all of these values for V and I. And some value at 0.7, it is 1 milliamp is given. Okay. So this value is given, let's say at 0.71 milliamp, but you are supposed to find out this value, this voltage and this current for the given conditions. So for this conditions, what ID and what VD, graphically it is this VD and this ID you have to find out. And what they have given is, in addition, they have given this value. Okay, but this value is not a solution. The solution of this circuit, the current that is flowing, is this VDID. But alone your diode graph, your diode, if you just plot for diode and you vary, right, then you will get this graph, this line. So the diode, at some point, it is saying that it will satisfy for this voltage, this is the current. But we have to find out in this circuit, okay, in this circuit, what is ID and VD flowing. So with that thing, so what it is showing here, so if you change R, right, the things will change. But for this R and VDD, it is always this ID and VD. And for some value of diode, that V and I is given. So that is what is given to you. And you have to find out that solution, as I just explained you, the operating conditions. So for that two equations only we'll be using. Okay, we'll be using that two equations. Sorry, yeah. I hope so. That is making sense to you now. And what it is saying, that as we had seen the V2 minus V1, right? And then the equation there. So the voltage drop, so that difference is 0.1 volt for a decade. So I2 upon I1 is what? 10. So when I2 upon I1 is 10, so this V2, this is given, so this is 0.1 it is saying, okay, for this I2 upon I1 is 10. So that's what it is telling in terms of equations, and if you imagine your circuit conditions. Now you have two equations and two unknown, because you have to find out ID and VD, and you know your two equations, right? So the first thing is, so we assume, so now what it is telling, now if you think, now what you have some, it is like initial condition, you can say, okay, so you are given some initial condition, and what is that? So you are so initial conditions are given that for this voltage this is the current, and so and you have to find out this two quantity, you have these two equations. So now what are we going to do? We will put these values with other initial, with other conditions VDD and R that is given, and slowly using two equations we will converge to this. So from these values that are given with other conditions, you will converge to this point. Okay, and when the values are same, as we will see, it is an iterating process where you converge and you find out this operating point. You understand what are we? So this same graph that you can see here, if you plot the graph and if you take this point, you can directly see. Okay, and the same thing you should be able to do by equation, and that's what we are going to see now. So this equation is the same representation of this graph. Do you understand, everybody? What are we trying to do? Then I will show you the steps. Samjhai che?
Yes, ma'am.
Okay, good. So now see, this is given, we assume this is given to you, that 1 milliamp for 0.7. So this is your diode satisfying thing, it is given to you, and we are using now these two equations. So ID, we have to find out that operating point VD ID. Okay, this is one of the condition that is given. So now with this ID and this VDD, right, you will find out 4.3, this is the current that you will find out. Okay, and now that you can use it here, that this is the equation where your V2 minus V1, like this way you have this equation, right? And in that it says that, so you can write down always because we have to convert, we have to find out that other voltage. If you know V1, right, so if you know V1, you have to find out V2. So now you will do V2 is equal to V1 is 0.7, you know that. So you bring it this time with this side. So V2 is 0.7, right? And then if you simplify 2.3 and VT, it is 0.1 log of what you found out. This is your what? This is I2 upon I1. So if this is I1 and this is V1, right? Then you have found out this is I2, and now we are finding V2. Right, but they both satisfy the diode curve. But this value doesn't satisfy your second equation, right? So now, so this values were for satisfying only diode curve. It was not satisfying your this equation, right? So this operating point is, it should satisfy both the equation. So now we are trying to converge and make sure that it satisfies this equation also. So now from this, we have to find out your V2, and you know the relation. So 4.3 upon 1. So you get this V2. Now that V2 and this 4.3, this V2, you will put here in this equation again. Okay. So here, so now it is ID is this your new, and this is so this and this are your new values, which you will put here, this new VDD minus this VD. That is this new value. This will remain same only. So you will get this new value, which will put here. So this is your I2, you will put here. Whatever you get is your this V2, the new value, which you will put here in VD. And then you do this process iterative. So then you get new ID VD, which again you do the same thing. And because ID did not, and then you find out that once you are doing, right, the values will converge. It will almost remain same. And then you can stop there and you can say that, okay, this is my ID VD, which is satisfying both of these equations, this equation and that, both, as I just talked to you while I showed you. And that is your operating point or the converging point, right? Because what was given to you was right, this 0.7 and 1 milli only satisfied this, right? And this will satisfy, this point will satisfy both these equations, this and this. And you were to find out this from what was given. So that's what we did. Right, so I hope that made sense to you. And this is your that operating point, a solution to your this circuit, ID VD. And this is the current flowing and this is the diode voltage. The values, last two values are almost the same. Okay. Okay, now any question? You can just think for a minute and tell me. You understood, right? Then I can go ahead.
Ma'am? And what was the use of that for every point, for every decade change in I, the voltage drop was 0.1?
Okay.
We didn't use it.
No, we used it. So let me tell you. So this was given to you. That's what, na? What was your question
Yes,
once again?
Yes, ma'am. We did not use this part.
Okay. Yeah, that was not needed. So see, yeah, you are right. See, what happens in your problem, whenever a question is given to you, but what it means is that this is the equation, and it says that for I2 upon I1, which is 10. So this term now, if you know that this is 10, this term is called everything, this is constant, and this will, and that V2 minus V1 is 0.1. That's what it is telling. Okay. So, but you are right. See, now that is very important when you are reading a question. There may be things that may be additional and not required. Okay. And you have to correctly understand the question, get the things that you want, and this is something additional, but it says it gives you an idea, okay, that if the difference is 0.1, then the current is changing 10 times, and here the difference is more than 0.1, it is 0.762, and it is 0.762, which is more than this difference what they have mentioned, right? So your current change should be more than, so I mean, just crude analysis, when you get your values, right, you can know that if your this difference is more than 0.1, so your current should change more than 10 times. Okay. So from 1 milli, you are getting this much milli. So of course, yeah. So for a decade change in, yeah, you are right. That is not used, it was not required. But as I said, that what I say is that when you read, there may be things that you need and not. So that is, you have to understand the question properly and use accordingly. And this is just an idea. Okay, that, see, this is also a measure. This device here is a diode, okay. but you will be studying BJT, and in your circuits, as I said, there is a MOSFET used. There are future nano devices. So this is a measure, you can say. And what does it say? See, at the end, it is a game of voltage and current. So input voltage you are giving, and you are getting a current, and that current, as I said, is a representation of your signal. That is the information that is propagated. See, information is passing through all the circuits. So that information is passing means current is passing. Okay. So always we need that in for an efficient circuit or low power. What you need is that, see, otherwise, as you know, current and voltage are proportional. If more voltage, more current. Right. So a measure of a circuit is that you give little voltage and get as high current as possible. That's the goal. Okay, so this is one of the measure that you can know for a particular device. So this is differing from device to device, and that is known. It shows the strength of the device, how good it is, and whether it will be able to process the signal or not, whether it will be able to drive the load or not. So this has an in-depth meaning, but as you said, correctly pointed out, this was not directly used. That is true, but it has a significance. Okay.
Hello, ma'am.
Apple.
Ma'am, in example 3.4, can you one show the slide?
When three, this one,
Here, 2.3 into N into VT, how approximation equal to 0.1 volt?
this,
Yes.
yeah,
No, yes, ma'am.
you take N as 1 and VT you have. Sorry, N as 2 here. N is taken. That will be given to you. N will be given how it is fabricated. So if you take N as 2 into then 2 and then 2.3, this with 2, right? You will
4.6.
0.1.
VT must be very small.
It is given now. We have done in the beginning. How much is
Yes.
VT? 25.8 millivolt
Yes.
at room temperature.
Means we have to take by default 25.8 millivolt.
See, it will be given. See, some values that are constant will be given. If not given, I mean, these are basic things you should know.
Okay.
Okay, it will come in BGT also. So when we did the diode equation,
Hello, ma'am.
દેખાય છે ને આ બધું slides તો I'm moving.
Ma'am,
See,
what?
VT equal to KT by Q. This is Boltzmann constant. This is degree Kelvin. This is electron charge. This is known as thermal voltage. At room temperature, it is 25.8 millivolt. Bolo.
Ma'am, what is N signifies?
See, this diode, no, it is fabricated. Where it is fabricated, it is known as foundry. Now, the way it is fabricated, okay, based on that, it will be N or N will be 1 or 2. The fabrication process, it is how it is fabricated. So that will be given to you. See, P and N, this is a semiconductor silicon. It goes through process of fabrication. And depending on how it is fabricated, it will be given to you. So, but you just understand that this is a fabrication-based parameter. Okay?
Okay, ma'am.
Okay. So now we saw diode and we saw the applications. Diode is basically a switch, as you can know, forward, reverse, bias, on and off. Okay. So now here is another application, and this is a making logical circuits. So digital electronics you have studied, where you will have inverter, AND gate, OR gate, any combination logic you can make. Okay, so that is digital circuit I'm talking about. And the rectifier, all these things what we studied was a power unit, which are analog circuits. Okay, digital is 0 and 1. And since diode is a switch, it is a two-terminal device, it is a switch on and off. You cannot make an amplifier, remember, okay, using the diode. It's not a transistor. It's a diode, means two electrodes. Two di means two electrodes, and on and off. So using this diode as a switch, you can make logical circuits, digital circuits. And here is an example of an OR gate and an AND gate. And as you can know, your gates can be 2 input, 3 input, right? So as you can see here, this is a truth table of your OR gate. This is a truth table of the AND gate. And this is 3 input, means 8 possibilities. If it is 2 input, 4 possibilities, you have combinations. And this circuit, as you can now, as it is tagged here, it is an OR gate. And this is an AND gate. So just look into this. Can you verify this truth table, whether this will definitely work as an OR gate or no? Your inputs are this A, B, C, and your output is here at Y. So does it work like an OR gate or no? So when all these 3 inputs, you can start with the first one. When all the 3 inputs are 0, then your output is 0 or no?
Yes. Yes, ma'am.
Yes, right?
Yes.
Because diodes are conducting or not conducting?
Non-conducting.
Not fun.
Not conducting, right? And your output is 0. Now let's say that any one is 1, or we can start with this as 1. This is 1 and this is 0 and other is 0. Both are, other two are 0. Right? So in that case, so 1 means you take it as 1 volt, let's say. Right? So if the first one is 1 volt and the other two are 0 volt, what will be your output?
And 1 volt.
1 volt. Because in that case, this is shorted, this is forward bias, this is not conducting, and this 1 volt will appear here, and your output is 1 volt. And similarly for any, if this is 0, 1, 0 or 0, 0, 1 or 2 or 1, this is 1, this is 1 and this is 0, right? Your output is going to be still high, and that's what we are following this thing for this combi, except for that 0 thing, right? Other things are obeyed. You agree or no?
Yes, ma'am.
Correct. So now let us see for the AND gate, and you start with 0, 0, 0. If all 3 inputs are 0, this is 0, 0 and 0, then are this conducting or no?
Conducting.
Conducting, very good. If it is conducting, means this point is shorted here. And what is this? 0 volt. And remember, this output is across the ground. There is a ground here. When you say an output, it is across this terminal and the ground. Right? And this is 0 and ground. So across 0 and ground is 0 volt. How about 0, 1 and 0, let's say? Hmm? No. One says
Everyone will conduct.
this is 5
All are
volt, this is 1 volt.
All are
Right? This is 1 volt, this is 0 volt, and this is 0 volt. Now, what you know, VB is 1 volt.
VA and
All are
VC
conducting.
will be conducting.
Do you
So
remember
0 will appear at VY.
initially we did The one which is more negative will be conducting. You don't have to forget anything. You remember this? I accept. See, this is 3 volt, this is 1 volt. So this is what? This will be conducting, this is more negative, ne? I actually,
Yes.
you remember this, then this is based on that only. Now what happened? This was more negative than this. A negative છે ને?
Yes, ma'am.
This is negative terminal, this is positive terminal. અહીંયા તો plus છે જ. But the one which is more negative will be shorted first. Like see, this 0 is more negative than 1. So this will be shorted and 0 will appear here, which will reverse bias this. અહીંયા તો 0 જ આવી ગયું. If any of them is 0 and you have a positive voltage, let's say it will be 0 because it is more strongly forward biased. 0 also, and the output is across 0 and ground. So 0 all. And then you have 1. બરાબર? So 1, બધા જ 1 હશે. If all are 1, then what you will have here? 1. 1 volt. Thank you. See, you have this diode, you have to understand the basics. And diode છે મારી પાસે, okay? And this is negative. Same, and I have another diode, same diode. Okay. Right? Same diode, I'm giving same voltage. I say 5 volt. Here also 5 volt. Both are, these are shorted, let's say. Both are short, nothing, sorry. Both are different. Let's say this is 5 volt. And this is also 5 volt. Okay, and I'm giving here same diode here, and I'm giving here one time 0 volt, and then here I'm giving 2 volt. Then which is more strongly biased?
One with the 0 volt.
So difference વધારે છે જેનું, right? So that is more strongly biased. So that's what. So if it is 1 and here it is 3, this is more strongly biased than this. The difference of the voltage you see, right? That's what. So that was on the same ground as what we had done before. And when you see the voltage, it is between this terminal and the ground, between this terminal and the ground, between this terminal and the ground. Okay, and how are all this connected? You must be knowing plus check if there is a battery, right? This plus means there is a battery here, this is plus, this is minus, and then this is grounded here. Okay, a minus share, a plus share. And similarly, when you are giving a voltage, it is a positive, right? Then you are giving a positive voltage, and there is a battery here, and then it is grounded. So ground is, I mean, when you connect a battery, there is a ground everywhere. And then, so that's, and the output is always across the ground. Okay. So with that thing, we'll move to one important topic, that is Zener, and a problem on that. It is a lengthy problem, but it is interesting and you will understand once I explain it. Okay, so if you can make AND gate or gate, then you can make any gate. So using that also you can make circuits logical, but we don't do so, right? Because now all the digital circuits are in an integrated circuit, and all these integrated circuits, they are made up of transistors, MOSFET. Okay. Sorry, just 1 second. It was an important call. 1 minute. Yeah, sorry, so many things going on now. Anyway, so without wasting further time, yeah. So this I have talked of this. Okay, so what is basically Zener and how it is different, all the physics and everything I have taught. I gave you an example also that this is basically to protect your circuit from fluctuations. So let's say when there is a fluctuation in the voltage, the current will change drastically, and this current may damage your device because this device they have a limited range that it can withstand. Okay, so maybe it can bear some maximum current or power. Right, so power is what? P is equal to I into V. So P is fixed. So if voltage is varying, current has to be less. So it has to obey that I, V or P limit. Otherwise, the voltage will be destroyed. Sorry, the component will get destroyed and you have to garbage that. So if it doesn't obey the VI or the power rating that it can withstand. Everybody has a limitation, right? The human body has a limitation. Extreme conditions we cannot take. Similarly for the device. And we had seen for an LED that if the LED is a 3-volt LED and if you give 5 volt, it will get destroyed. So what we do, the Zener is a protector here. And that's what it is extensively used because all the this electrical signals, they are by by nature fluctuating, and it's not that they always fluctuate, but you cannot predict and they can fluctuate. Okay, so we have to be ready and we have to ensure that the circuit is safe irrespective of the fluctuations happening. Do you understand this much?
Yes, ma'am.
मैं unmute કર્યું ને હા. So that we have to ensure. Now, the nature of the Zener is that it is a protecting device which will protect your whole circuit, and if connected across the load in parallel with the load, then now as you can, if you recall that 3-volt Zener will be on only. If you just recall this, because these basics are very important, otherwise you won't understand this. If you've forgotten, I'm just moving here. So if this is a protector, now this is a 3-volt LED. Okay, this is 3 volt. If you are giving 3 volt, it's okay. But if this is fluctuating and goes to 5 volt, this will get destroyed. So what we do, we'll have a 3-volt LED across the Zener across this. If the voltage below 3 volt, okay, this is off. Below 3 volt, it will be off. And your LED will only get 3 volt. But once it goes above 3 volt, right, 3.145, whatever the volt, this will be on. The Zener will be on. And irrespective of then, if this is a 3-volt Zener, then if the voltage is 4 volt, still this across this, it will give 3 volt only. Okay, so this guy will get 3 volt if the Zener is connected because it's a 3-volt Zener irrespective of the fluctuations happening here. And this is the nature of the Zener. When I say 3 volt, it will be conducting at 3 volt. It has already it works in the breakdown region and it is in the breakdown and it is conducting, and it is at a 3 volt. That's what it means. And then even if the current is still, now see, this is the voltage is changing, the current will change. Even if the current is increasing, right, it will still, the voltage will remain same. So that's what, this is the I. Even if I is changing a lot, V will remain same. I is here, I is here, I is here, but V is almost the same. So that's the beauty of the Zener. It is a protecting device, it protects your circuit. And here we will see an example where you will understand the beauty of this device. And this is the model of the Zener. That this is, what is this? See, this is VZ0, this is VZK. So from this voltage VZK, it will start to conduct, and this is the breakdown Vz. So this will be given that when it is conducting. So this is the conducting voltage. Here exponentially it is rising, and it is risen to Vz. And this is for some test current that you get is VZK. This is Zener knee. The shape is like the knee. I'm just repeating what we have done before. And for this particular Vz, right? So this is the current that is flowing for some Vz. And what you see here is that if you draw, so this is a linear line, and where it cuts here is VZ0. Mostly VZ0, there is little difference, right? There is a little difference, but they are almost the same still. And even if the current is varying by delta I, right, delta V is very little, right? And then how it is given, this variation because of delta I, there is a variation of delta V. The slope of this, okay, the slope is it is equal to the inverse of the resistance. The slope means there is some resistance. So this slope is equal to this inverse of this RZ when you take the ratio. So this is, and where it goes, it's VZ0. And delta V, the change in the voltage, okay, sorry, the change in the voltage is equal to delta I into RZ. And this is the model of the Zener. As you can understand, this is VZ0, RZ. When I did Zener, let me go back. Right, so this is the same thing when we did Zener. I just had explained you here that, so this is delta V is equal to delta I into RZ. This is the change. And you can, this VZ0, right? This is VZ0 here. So here VZ across Zener, what is the voltage? It is this voltage plus this change. Okay, so that's what, so that is VZ0, okay, plus IZRZ. So this is the IRZ, this is RZ, and the current that is flowing is IZ. So that is the current that is flowing, that is this IZ. So this Zener, which is this, now see, this is a symbol. If you want to analyze your circuit, you cannot keep this symbol. We have to have an equivalent model of that. And this is the equivalent model given by this supply, which is constant. That is this VZ0. Okay. And then depending on the current, right, that will be the change IZ into RZ. So the Zener, the voltage across the Zener is this fixed value. This will be given in the data sheet, this one. IZ will change according to the change in the load conditions. Okay, so you will soon understand. So this is the current passing through the Zener, and this may change because of the conditions external. And that's why this the whole VZ will change, but this will remain same. It is there in the data sheet. And VZ is equal to VZ0 plus RZ IZ. So this much you have to remember. How IZ is changing, let me show you in this example. So as you can understand from your AC mains, right, there may be fluctuations and it will go to any of your electronic circuit. So let's say this is your AC main. Okay, you think like this way. And through this resistor, right, this is the load where your this AC, you are giving a AC voltage, and because of that the current is passing, which will go and it will be delivered to the load. Now let's say that there is some fluctuation here, then it should not happen that this load will get. So this load RL, what it is an input. It is an, so here in that what we saw was LED. I just, in that example that I showed you, it was LED, right? But this is a circuit. It can be your phone charger, your TV, your refrigerator, any load. Okay, and you want to protect that against the fluctuations that are happening here. So across this, as you remember, recall that LED I just showed you. So think that as an LED, but this is an input resistance of the next stage, the circuit. Okay, and through to this in parallel, this Zener will be connected. So this is how it is, and we just understand the problem. And if there is a fluctuation here, then how much change in the current will happen at the load? Okay, that's what we want to see after the Zener is connected. Okay, so some things are given, the Zener value is given, it is a 6.8 volt Zener, means it is conducting at 6.8 volt, and this is the circuit that is given to you, and this is subject to fluctuation 10%. So if it is 10 volt, it may go to 9 volt, and it may go to even 11 volt also. Okay, and this is the equivalent of the Zener, that because when you want to analyze, you with this symbol you cannot analyze, so you will put this VZ0 and this RZ. Okay, and again, as I said, it is all a game of I and V that we have to calculate, and we are going to understand what is given and what we have to find out. But the overall meaning you understood, right?
Yes, ma'am.
Okay, so here it says that a 6 volt Zener diode in the circuit below. So this is 6.8, as we saw it was a 3 volt Zener to protect the LED. This is a 6.8 volt for this load here. And this is given, VZ is 6.8 volt. This is the Zener. IZ is given, RZ is given, and IZK is given, and V plus is this. So now when all of these things are given, that you have to think in mind. Now if you replace this with this, right, then this, from this loop, this is the total current, and it is, if there is a load here, if there is no load, then this I will be equal to IZ. But when there is a load, this I current will get divided into this Zener current and the load current. Okay, so this IZ is given, this IZ is given, and this RZ is given, and VZ0 is not given, but if this is given, we can find out VZ0 also. And as we move ahead, I'm just going to explain you. And then IZK is 0.2 milliamp. So in that IZK, as you had seen here, where is IZK? This. Okay, so that is given. So now what it is asked, determine the following quantities. This is the first thing. Find V0 with no load and V plus at nominal value. So if it is 10 plus or minus 1 volt, 10 is the nominal value. Okay, understand that. And find V0 with no load. So now you have to find out the output voltage when there is no load. So this V0 without this. So if the load is not there, IL is also 0. Okay. So, and the equivalent circuit for the reverse bias operation of the Zener diode. So find V0 with no load. Okay, with no load and nominal. So that is V voltage supply is 10 volt. So in that case, this will be an equivalent circuit because there is no load, and the Zener voltage across here is your V. This is your V0, right, as shown here. So now from this terminal to ground is your V0. So this is a simple case, and right. So here, what you will do first, the diagram. Yeah. Okay. So first, as you know that this is your equivalent circuit, so you have to find out VZ0, and you know this VZ is equal to VZ0 plus RZ. So from that VZ0, VZ was given 6.8, RZ, IZ is given to you, R is 20 and I is 5 milli. So from that VZ0 you can find out. Okay. And note that the supply voltage can fluctuate by plus or minus 1 volt. Imagine this fluctuates as a random process. Okay, you don't know when it, at what time it will happen. So now what you have is a simple thing. This is 10 volt. It is given to you. This is also given to you, right? And VZ0 we found out it is 6.7. I you have, and then this also you have. So you can find out this V0. Now V0 is equal to what? It is 10. See, VZ0 you can find out two ways. This voltage plus IZ into RZ. Or it is 10 minus IZ into R. But that IZ is varying. Okay. So that IZ you have to find out. That IZ1, see this IZ1 milli was for this condition. See this IZ 5 milli. Okay, it is when it is conducting VZ at 6.8 volt. Now see that I just think of the graph that IZ. So now in this condition, what is IZ? So that you have to find out. IZ is equal to 10 minus this voltage divided by the total current. So this, that is IZ is this much now. And 10 minus this. So when, see what is changing is because of this voltage, your IZ is changing. Okay. So so we found out that IZ from all the other values, and that's how you managed to find out V0. Or once you have IZ, it is IZ into RZ plus 6.7 volt, and you will get 6.83 volt. So without any load, this is 6.83 voltage that you get. Okay, so that is, if you think in terms of this diagram, what was given to you is that at some voltage, okay, that is this VZ, this was given to you. And this is at some voltage, this is your Zener voltage, but now this is fluctuating, okay, that I is varying. So in that case, how much is the, if this is the, this can vary a lot, but your voltage will vary only little. So that change, but here it is simple, nothing big deal. Again, understand this is the equivalent of this. And VZ0 you put in, RZ is given to you. So yeah, and so this current, okay, that you used, because that is, this is the relation, VZ is equal to this. So in this relation, this is your Zener current when it is operating. You will put this 5 milli here to get VZ0. Okay. So you got this VZ0. And now this is your circuit where you will have a current that is flowing. So this is I, it is going as IZ and it is going as IL to the load, but now load is not there. So everything is flowing through this loop only. And that is your IZ current. But with these conditions, what is your current? That is what you have to find out first to get that voltage. So now the next part of this, find the change in V0 resulting from this plus or minus voltage, this plus or minus 1 volt change in V plus. So now We have to, so now here V0 was what? This much. When it was a standard voltage, 10 volt, what your circuit is designed for. But sometimes it goes to 11 volt and then 9 volt. Then what is the change here? That's what we have to find out. Okay, so we'll go ahead and you have to figure out how much it is. So in that case, as you did here, now because instead of 10 volt, it is 11 volt here now. And because it is 11 volt, your I will change. And because your I will change, current will change because the voltage has changed here. More voltage, more current. And because of the change, and if less voltage, then this I will lessen. And because of the change, there is a change in the output voltage. Okay. If I is changing, then the voltage across these two terminals will also change. And that's what it has said, that for the positive and the negative. So this is the variation 11 to 9. Okay, so if it is 11, right, your V0 will be this. So what is this here, what you got? This is your IZ, okay, and the same thing that we did here. Okay, 10, so instead of 10, it is 9 and then 11, same thing. So 9 and 11, and this will be your voltage if it is 11 volt, 6.865, and here it was 6.83. So this is, when it's 11 volt, the voltage developed across here will be 6.8, 10 volt, it is 6.83, 11, 6 point, here it is 83, it is 6.865 and 6.7. So you can see that from this 6.83, so 6.83 is in between for 10 volt. So अगर थोड़ा ज़्यादा है तो this is not much, 6.83, and see the difference. Okay, so if you take this maximum difference of this minus this, it is 0.77 volt, or this is how much? 77 millivolt. Okay, and if you divide by 2, because this is plus minus 1, it is plus minus 38.5 millivolt. So this is the change from the nominal value. So itna hi change hoga output voltage mein, it will keep almost constant. That's what it means, or it shows here. And then there is a parameter that is known as line regulation, which is defined by delta V0. So output में कितना change है for a change in the input. Okay, and this should be as low as possible. And here you can see this is a little value. Delta V0 is this much. So that is delta. So change, pura change. So that is 0.77. Okay, and divided by 2 volt is the change in the input voltage, 11 minus 9. That is 38.5 milli. Okay. So this is the definition of line regulation. This kind of things are used in transmission line just to make sure of the stability, that how much it is varying, even if the input is varying. And you can see that because of the Zener, the output, even if the input changed by 2 volt, right, the output only changed how much? So 9 to 11, if it goes, then the output will change by not 77, it is just M here, 77 millivolt. So 9 se 11 jayega, your supply, still your output will change by 77 millivolt. That's what it means in simple way. Okay, is that clear? Now there is no load, but this Zener is meant for a load. Right? Zener is not the load. It is to protect the load. So now we will see what happens when there is a load. Do you get it? So that's the next step.
Yes, ma'am.
समझाई छे? Okay. Then afterwards you may think patiently and calmly when you are working, sitting alone. Just understand, try to. Okay. So now there is a load. So find the change in V0 resulting from connecting a load of RL with a, see now here there was no load, and you found out with 10 volt, you found out V0 without any load. Now it is saying that here I have 2K load, then what will be the V0? Okay, so that's what we have to find out with the load now. And that load may vary also, 2K, 3K, whatever. So now what is happening is that, so this is your, so with whatever is given, this will be your circuit. The load is across the Zener always. And as you can see now that your current which is flowing, it will be divided into IZ and IL. And this IL is nothing but it is delta IZ, because because now when there is a load, some current is stolen from the Zener, because this is the total current. If this was not there, this Zener was getting all the current. But now this is there, so some little is stolen from the Zener. And how much it is delta IZ, as we had seen here in this equation. Right, this delta V is equal to delta IZ RZ. So IL, load current, is nothing but the change in the Zener current. So here, yeah. So here IL, first of all. So when so now another thing, just think that of that LED, okay, that LED example. Just think of that LED example where your LED was conducting at 3 volt. Okay, sorry, your LED, when the voltage was high, your Zener, 3 volt Zener was conducting at 3 volt and your LED was on. Okay, you think this as an LED. Okay, so this is a Zener with 6.8 volt. So now we have to find out first what it is asked, and find out the change in V0. So how much is this V0 with this load when you compare it without load? Okay, so the thing is, it has to find out this IL. And how much is this IL? We know that this voltage, because Zener is there, it is a 6.8 volt Zener. So it is this voltage we already have divided by, so this voltage is appearing here also. This is the same connection. Okay, so across this resistor is this 6.8 volt. That's same like the LED. And LED had 3 volt. So this is 6.8 volt. And divided by, so this is IL. So this is the IL that is flowing, and that is 3.4 milliamp. Now this IL which is flowing is 3.8. Is this value correct? Because if it is only correct when it is less than IS. Okay, so that's what we are trying to find out, that what will be the IS. So IS is simple. We have the voltage here across the Zener. So 10 minus 6.8 divided by 500, 6.4. So IS is 6.4 and then IL is 3.4. So this is much higher than this, and this is making sense. Okay, so this is reasonable value because IL is less than IS, and it should be. And what you can say here is that delta V0 is equal to RZ and then delta IZ. And since delta IZ, now what is delta IZ? Is IL, as I said you in the beginning. This IL is nothing but the change in this. So this IL that we found out is delta IZ. So this IL which we found out is delta IZ. So that is this. So now the change in the voltage is how much delta V0 is RZ into this. So this is delta V0 is the change, that is minus 68 millivolt. Now you can see this is also a small value in the change in the output voltage. Okay, because of the load. So this is minus 68 millivolt, is delta V0, the change in the voltage, this delta V0. So the same graph, if you see here, it means the same thing, is equal to delta I. That delta I is, so this is with respect to Zener, how much change. So the voltage, that delta V, it is across the Zener only, which is going to the load, but it is also across the Zener, across the load, it is in parallel. So this delta I you see here, that is what we calculated. And then RZ is given. So this is the change, delta V. So this is delta V from here to here. So this point, and then what it is now conducting. So this is delta V for this change. So before it was Vz, now this is V, so here it is delta V here. So it is the difference between the tangent at this point. So this is the tangent here. But if you take a straight line, it is your Zener voltage, Vz. Okay, and so this is, so in short, it is, let me show you this way, that for this current, this is the voltage. This is the voltage. Okay, and now you are at this current, that is this current, right? This voltage, if you have a straight line, it will fall somewhere here. So this little change, okay, is delta V R, delta I, and this is huge. So in terms of that, here what you see is that, so the voltage change is very less. And it's like line regulation, there is a term load regulation. Okay, and what does it say? It is the ratio of the change in output voltage. Output voltage changed by this for the change in the load current. Now, what was the load current? That is initially before it was 0, so that is the load is 3.4 milliamp, we found out. Okay, so you take this ratio and it is 20 millivolt upon milliamp. So this are, but the main thing is you have found out the change in V0, which is really small. It is in millivolt. So it's, okay, so this is just to explain you so back that it shows you that when you have a Zener and irrespective of the load, right, the change in the voltage is very less. Even if there is a change, for a huge change here, there is a little change here, in short. Okay, that's it. The time is already up, right? I cannot start a new topic. So the next time what I'm going to show you